Okay, so we have seen what a demand meter is and how the demand meter measures the maximum demand and demand for a month. So we'll use an example to demonstrate the use of demand meter or how demand meter calculates the electricity bill. So please see this figure, this figure. What is shown here is the active power drawn by a large factory between 7 and 9. Okay, 7 and 9. So for 120 minutes, this is for 120 minutes. Okay, now the demand meter has a 30 minutes demand interval. We have already explained what is demand interval, the interval at which the demand is average demand is measured. So let it be 30 minutes demand interval. Now, and this is 7 to 9 a.m. Okay, this is for morning. Now, let's assume that at 7 a.m. the first pointer of the demand meter reads 2 megawatts. First pointer of the demand meter reads 2 megawatts. Okay, while we know that we have two different needles for the demand meter, or two different pointers for the demand meter. So the second pointer reads, or it indicates 3 megawatts. 3 megawatts at the same time. Okay, so second pointer at the same time. So at 7 a.m. Okay, so this is the reading. Now, what are the meter readings at the following times? That is what is asked. A 7:30, B 8, C 8:30, and D 9. So for all these times, you are asked to find the meter readings for this demand meter, which shows 2 megawatts at 2 megawatts on its first pointer at 7 a.m. and 3 megawatts on its second pointer at 7 a.m. at the same time. Okay, now we have to find the meter readings for these times 7:30, 8, 8:30 and 9. Seeing the plot given, this is the plot given. Active power drawn by a large factory between 7 and 9 a.m. Now, according to this graph, what can be the average power or average demand between 7 and 7:30? Because you are asked to find the reading at 7:30 in the A part. So what is the average power or average demand between 7 and 7:30? It is 2 megawatts, right? It is 2 megawatts. From the plot, it is 2 megawatts. So the pointer 1, what will be this is pointer 1. Pointer 1 reading will be, it continues to indicate 2 megawatts, right? So P1 would be 2 megawatts. P1 would be 2 megawatts at 7:30. Okay, at 7:30. And what about pointer 2? It stays where it was. It is at 3 megawatts itself because it has not seen a higher demand. Right, it stays at 3 megawatts itself. So P2 would be equal to 3 megawatts. Now, what about the average power between 7:30 and 8 from the plot? 7:30 and 8. But you can see that from 7:30 to 8, it differs. It has some fluctuations. So to find the total megawatts, we need to find the energy and divide it by time. Find the energy and divide it by time. So to find the energy, you have to multiply megawatts with the corresponding time interval, because this is not uniform. For this interval from the plot from 7:30 to 8, the power consumption is not uniform. For different time frames, we have different power consumptions. So accordingly, we have to multiply with the power. So I'm going to find the energy now. So it is for this one. Okay. 7 megawatts for 5 minutes. Then what else? Plus 7 megawatts for 5 minutes from 7:30 onwards. Okay, from 7:30 to 8. I'm calculating for 7:30 to 8 interval. Then 2 megawatts again for 5 minutes. 2 megawatts again for 5 minutes. You can see here, this is 7 megawatts for 5 minutes. Then 2 megawatts for 5 minutes. I'll change the color. This one, this one. Similarly, I'm going to find other power consumptions also for other time frames till 8 AM. Okay, now plus 4 megawatts for 20 minutes. So this will give me the total energy consumption from 7:30 to 8. If I divide this by 30 minutes, I will get the power, which is equal to 4.17 megawatts. You can check it, 4.17 megawatts. So during this 30 minutes interval, pointer 1 gradually moves from, it was at 2 megawatts earlier. So now it gradually moves from 2 megawatts to 4.17 megawatts. Now at 8, both pointers indicate 4.17 because the maximum demand is also changed. You know that the demand meter has a second pointer, which is the maximum demand pointer. That also is 4.17. So this is P1, this is P2, pointer 1 and pointer 2 at 8. Now comes 8:30. What about 8:30? The demand between 8 and 8:30, we have to find again from the plot. How will we find it? So 8:30 I'm taking 8:30. So PD is the demand, 7 into 5 from the plot. Okay, let's check the plot. I'll show both on the screen. Here is the plot. You can see the plot when I'm writing the values. Plus 8 into 5 plus 4 into 5 plus 3 into 5 plus 5 into 5. Then because a lot of fluctuations are here in 8 to 8:30 frame. Okay, in 8 to 8:30 frame. This is one power, this is another power, this is another power, this is another power. Right. So 5 into 5 plus 1 into 5. So this will give me the energy divided by 30 minutes. So that is equal to 4.67 megawatts. So again at 8:30, both the pointers have moved up from 4.17 to 4.67. So this is how we find the demand meter, how the demand meter measures the maximum demand and the demand, average demand during a time period. So similarly, you can find it for 9 also. That I'm not writing here. You can find it. Now we will move on to tariff based upon power factor. As I already told you, we have AC machines such as induction motors or transformers which absorb reactive power to produce their magnetic fields. So the power factor of these machines would be less than unity, and consequently the power factor of the factory itself, factory in which they are installed, that itself will go down. So a low power factor increases the cost of electrical energy. That will be demonstrated by another example. So let's consider two factories X and Y. That is what is shown in this figure here, X and Y. Okay, this figure. Now you can see this figure. So in that figure, what is shown? It consumes the same amount of energy. Both the industries consume the same amount of energy in kilowatt hours, both X and Y. And in addition, they have the same maximum demand in kilowatts. You can see it's 1000 kilowatts here. It's again 1000 kilowatts. I think it's 1000 kilowatts here also. Okay. However, the power factor of X is unity. The power factor of factory X is unity, but the power factor of Y is 50%. Power factor of Y is 50% power factor here. This is unity, 100% power factor for X. So based on this, if we are going to find the electricity bill, the energy and demand being the same, here you can see the energy and demand being the same, the watt hour meters and demand meters will show the same reading at the end of the month, because this is for 30 days, end of the month. Okay, they will show the same reading. So it would appear that both users should pay the same bill. However, we must not, neglect the fact that the apparent power drawn by each plant is different. Apparent power is in kVA, right? That apparent power drawn by each plant is different. How will I find the apparent power drawn by factory X? Apparent power is represented by S, which is equal to P divided by cos theta, which is equal to 1000 divided by 1 for factory X, which is equal to 1000 kVA. Right. Now, what about apparent power drawn by factory Y? So this is for factory X. For factory Y, it is S equals again P by cos theta, which is equal to 1000 divided by 0.5, which is equal to 2000 kVA. See the difference. First one is 1000 kVA, second one is 2000 kVA. It's almost double. And we know that the line current is proportional to the apparent power. So the factory Y draws twice as much current as factory X. And the line conductors feeding factory Y must therefore be twice as big, ideally. See, normally if two factories are being fed by lines, then the lines will have such specifications. The specifications will be already taken into consideration, but this is just for the sake of demonstrating this particular concept. So the line conductors feeding Y, factory Y, must be twice as big, right? Then the transformers, circuit breakers, disconnect switches, and other devices supplying energy to Y, it must have twice the rating of those supplying X. So in general, the infrastructure cost is more to feed energy to factory Y, as its power factor is half the power factor of factory X. Then the utility company must invest more capital to service factory Y, and consequently it is logical that it should pay more for its energy, even though it consumes the same amount. So you can see here the 1000 kilowatts is same, right? The 1000 kilowatts is same, then the energy is same, both demand and energy are same, but because of the power factor, this comes into picture, right? The problem is with kVA that reflects on the line current. So that is what we have understood from this particular example, the importance of charging in kVA terms for industries. Okay. Now we'll move on to the next example to see the typical rate structures, and we'll calculate the meter reading for some industries. Let's take a 1 minute break, then we'll continue with the next lecture. Thank you.